Welcome to Efiwe, excellence without stress.
Hi, dearest Efiwe's. We are back again. It's me, Miss Stella, your favorite physics tutor, your favorite tutor in general, and we are back again on this our journey. We're back again on this excellence without stress part we'll be taking for a while. And today we're going to take another very interesting topic in physics. You know, I told you every topic in physics is very, very important, is very interesting. And today we're going to Newton's laws of motion. Newton's laws of motion. So let's just start by defining force. We believe that force is the interaction between two objects that causes a change in the motion of the objects. So interaction between two objects that causes a change in the motion of the object. You know, we want to talk about motion because this is Newton's laws of motion. So what is a force? Actually, interaction between two objects that causes a change in the motion of the object is what is called force. So what impact can forces have on objects? It can make it move, it can make it speed up, it can make it slow down, it can stop it, it can cause it to change direction, and it can also cause it to change shape. So in what way does the mass of an object impact force? Is there a relationship between mass and force? Definitely there is a relationship between force and mass, because if you remember, force is mass times acceleration. So it means that mass is directly proportional to what? To force. So mass affects the impact of force. Mass affects the impact of force. If you want to fight someone that is very, very big, you want to push someone, you know, if you push someone that is 5-year-old and someone that is 50-year-old and a 50-year-old man, to push, okay, let me not say 50, let me say a 27-year-old man. If you want to push a 27-year-old man that is strong, that works out, or you want to push someone that is just a baby, you know that the force you will need to impact to make a difference in a 27-year-old will be far, far more than the one you use to push a baby and make the baby to change its or her procedure. So that is it. So in what way does the mass of an object impact force? So mass impacts force because mass is directly proportional to force. For you to affect force to have an effect on the mass must also increase. So let's proceed very quickly. Then we have when a force is applied to an object. Anytime you are talking about force, just remember what you do when you lift something from where it is, when you push something, when you carry something, you are applying force to that thing. So when a force is applied to an object, it will result in a change of momentum. Momentum is mass times velocity. Momentum, the mass of the body, and its speed is what is called the momentum. If you want to talk about your momentum, you're talking about how fast the mass of the body and how fast its velocity is. So momentum is actually mass times velocity, and the unit is kg/ms minus 1. So this change may involve a shift in velocity, such as an increase or decrease in speed or change in direction. So this increase or decrease is what is called the impulse. So an impulse causes a momentum change. So the formula for impulse is force times time, force times the change in time, and it's also equal to what? The momentum change, that is the mass times change in velocity. Remember that momentum is mass times change in velocity, and that gives us the relationship between impulse and velocity and momentum. So impulse is equals to momentum change. So now we're going to Newton's laws of motion. So Newton has three laws. We have three Newton's laws of motion, and they are very applicable in our everyday life. So the first law states that every object continues in a state of rest or of uniform motion in a straight line unless acted upon by an external force. That is actually so true. The first law states that every object continues in a state of rest. It will continue in a state of rest until or of uniform motion in a straight line unless acted upon by an external force. So that is Newton's first law. So Newton's first law explains why passengers in a fast moving vehicle tend to move forward when the car suddenly stops, or to be pushed backwards when the vehicle suddenly speeds off, since there's little or no force to restrain them. So you can see from here, an object at rest will remain at rest unless someone comes to push this ball. If there's no effect of wind, there's no any other thing on it, if this ball is at total rest, it will continue to be there unless acted upon. Have you seen it? The foot by an unbalanced force, and the object is continuing in motion. You see this foot now, pushed the ball and the ball continued to be in motion, and it will continue to be in that motion unless acted on by an unbalanced force. Have you seen that this force is what is going to stop its motion? So this can allow it to move a bit far backward. So that is Newton's first law of motion. The first law states that every object continues in a state of rest or of uniform motion in a straight line unless acted upon by an external force. So Newton's first law explains why passengers in a fast-moving vehicle tend to move forward when the car suddenly stops. So what is inertia? The tendency of an object to resist a change in motion. You get, sometimes when maybe you want to go to school, you want to it's school period and you have to wake up early, and your mommy comes to your room and knocks and says stand up. Most times you want to be in that your state of rest. You don't want to stand up. So the tendency of an object to resist a change. I don't want to stand up yet. The weather is cold. I still want to be sleeping. So inertia, the tendency of an object to resist a change in motion. This means that an object will either stay at rest or continue moving. You don't want to leave that position you are. Either you are at rest or you are continuing in a motion. So, or continue moving in a straight line at constant speed, and that is inertia. So this is Newton's first law. Very easy to explain, and it's something you can really apply. Even with the picture we put there, a body will continue to be at rest or in uniform motion unless acted upon by an external force. Then we have the Newton's second law of motion. I'm sure that this force is equal to mass times acceleration is not new to us at all. No, it is not new. We've come across it so many times. So what is Newton's second law of motion? The second law of motion states that the rate of change of momentum, don't forget momentum is mass times velocity, is proportional to the impressed force and takes place in the direction of the force. So don't forget that the second law of motion says that the rates of change of momentum, the rate, when you say rates, that is momentum divided by time. After that, anytime you hear rate, just know that time, rate is time divided by whatever quantity they are talking about. So when they say the rate of change, it means momentum divided by time. So the second law of motion states that the rate of change of momentum is proportional to the impressed force and takes place in the direction of that force. Newton's second law enables us to define an absolute unit of force which remains constant under all conditions. And so now we have the constant unit, which is force is equals to mass multiplied by the what? Acceleration. Mass multiplied by the acceleration. You remember that we have this. Force is directly proportional to the change in momentum divided by the what? Time taken for the change. That's why that's what it means by, that's what they mean by the rate of change of momentum. The rate of change of momentum, which is mass times velocity divided by time. And that's why we have this formula. F is directly proportional to the mass change in momentum. So this is mass times the final velocity minus mass times the initial velocity divided by time. The starting velocity. Most times you say a body is at rest. The initial velocity is 0. Then you say, okay, it's accelerated to a velocity of 550 meters per second. That is the final velocity. So this is the formula that F is directly proportional to the change in momentum divided by time. So you know where m, u, v, t are mass. You know m is the mass, u is the initial velocity, v is the final velocity, and t is the time of motion of the body acted upon by a force. And you know, when we have a proportionality sign, you know, we have to change to equal. So don't forget that v minus u over t is what? Is your a. Remember that, because this is change in momentum. So m is equals to v minus u over t. V minus u over t is a. So we can say F is directly proportional towards MA. So A is equals to V minus U over T. Don't forget, if we are introducing an equals to in place of the proportionality sign, we bring a constant. So where K is a constant and the unit of force is chosen so that K is always 1. So we don't use the K is 1. Hence we can write that F is equals to MA. So the Newton's second law of motion gave us the formula for force, and force is mass times acceleration. I'm sure we can get our mass times acceleration from everything we've explained here. So this is an example. A constant force of 5 Newton. A constant force of 5 Newton acts for 5 seconds on a mass of 5 kg initially at rest. Calculate the final momentum. Calculate the final momentum. So this is the first example. 1. A constant force. So we have a force of 5 Newton asked for 5 seconds, so we have our time on a mass of 5 kg initially at rest. So I told you when a body is initially at rest, it definitely means that the body was the initial velocity is what is 0. So they said we should calculate the final velocity, the final momentum. Don't forget, F is equals to mass, right, times V minus U over T. Is that not so? Where V is your initial velocity, V is your final velocity, U is your initial velocity, and T is the time taken. So don't forget, when the body is at rest, U is equals to 0. So what is going to happen to this? M multiplied by V. Let's go to our board. You know, we have it like this. We already said that our force, right, is equals to M, right, V minus U over T. And you notice all of this is just as if I'm saying F is equals to what? MA, right? So I can write this also as F is equals to MV, right, minus MU divided by T. And in this case, they said the body was starting at rest. So this part will have to go because U is equals to what? 0. So what will be left? We're going to have F is equals to MV divided by the what? Divided by the time. Divided by the time. So let's check. Divided by the time. And what is our force? Our force is 5 Newton, time is 5 seconds, and the mass is 5 kg. So everything 5, 5, 5, right? So we can do the 5 because we are looking for our velocity, right? So that's equals to 5 is equals to 5V over 5. Is that not so? So 25. So 5V is equals to 25. V is equals to 25 over 5. Then V is equals to what? 5 meters per second. 5 meters per second. So that is the final velocity. That's the final. So this body now, with a constant force of 5 meters, acts for 5 seconds on a mass. Initially at rest, calculate the final momentum. You know, momentum is the mass with its velocity. We've already talked about velocity in most of our classes. We know that velocity is what? Displacement divided by time. Displacement divided by time. So look at it, and we got our what's it called? The final momentum to be. Oh, the final momentum to be. Okay, we got this final momentum we are looking for. Sorry, not the final velocity. So we got the final velocity. We got the final velocity to be 5. Then from getting it as 5, what are we going to do? We're going to get our momentum. The momentum is mass times velocity. We're not asked to look for the final velocity. We're asked to look for the final momentum. And we know that momentum is what? We know that momentum is what? Mass times the velocity. And the mass was 5. The velocity is also 5. And that's equals to 25 kg. ms minus 1 because n is in kg, v is in meter per second. And so we have the final answer for that. We have the final answer. So the next question says, a jet develops a thrust. Thrust is the force of 270 Newton when the velocity of the exhaust pipe, when the velocity of the exhaust gas is relative to the engine is 300 meters per second. What is the mass of the material ejected per second? What is the mass? So what were we giving? We're giving the thrust, we're giving the velocity, and we were asked to look for the what? The mass. So you remember that F is equals to MA, and your A is what? V minus U divided by T. Okay, we were giving the thrust. The thrust is the force multiplied by the time. That is why it is Newton second. So the thrust is Newton second. So we're giving the thrust, and that gives us our FT. And our FT is what? Impulse, force times time. So they give us the impulse, which is the force times time, when the velocity of the exhaust gas is relative to the engine is this. So from here now, F is equals to MA, MV minus U minus MU over T, right, is equals to what? FT. I'm sure we can get that. So let's go to our board to do that. So since we have it like this, we have F, we have F to be equals to M, right? V minus U divided by T. If I cross multiply, I can have it as FT is equals to what? MV minus what? MU minus MU. So this F multiplied by T, which is the impulse, was what we were given, because we were given 270 Newton second, and that is the thrust. And that is the thrust. So impulse is equals to what? Force times time. So we have this now. So it's as if we're saying 270 is equals to mv minus what? Mu. Mv minus mu. So let's check what we're asked to look for the mass. So we're asked to look for the mass. We're asked to look for the mass. We're given the what? The velocity. And a jet engine develops a thrust of 270 Newton second when the velocity of the exhaust gases relative to the engine is 300 meters per second. What is the mass of the material injected? What is the mass of the material injected? So from here, let's do that. Let's continue. So we have this now. We assume that our initial velocity is 0. So we have that Ft, right, is equals to what? Mv. Is that not so? So Ft is equals to Mv. So, and V, we are looking for our M. M can then be equals to Ft over V. So Vn will be equals to what? 270 divided by 300. 370 divided by 300. So we have that. So 270 divided by 300, and the mass was 0.9 kg. So a jet engine develops a thrust of 270 Newton seconds, and that is the impulse. Force times time, impulse, when the velocity of the exhaust gases relative to the energy engine is 300 meters per second. So with this relationship, we were able to get the mass of the jet engine. So now the Newton's third law. So we've talked about Newton's first law, and Newton's first law was telling us about what? That a body will continue to be at rest or in uniform motion in a straight line unless acted upon by an external force. We went to the second law, which showed us the relationship between the force and the momentum and the change in momentum. Now this is the third law. Newton's third law of motion. The third law of motion says that action and reaction are equal and opposite. Or to every action there is an equal and opposite what? Reaction. If you study well, you will pass. If you pray, your answers will be answered. If you obey your parents, they will be happy with you, and so on and so forth. Action and reaction are equal and what? Opposite. Equal and opposite. You can see the swing. As the swing is going back, a force is going to be pushing him back. Once you are pushing yourself forward, another opposite force will actually be doing the same thing. Equal and opposite. Don't forget that the third law of motion states that action and reaction are equal and opposite. Or to every action, there is an equal and opposite reaction. This law is fundamental in understanding interaction between objects. It helps to explain how things move, why rockets can launch, and how everyday objects interact with each other. The law implies that when a body A exerts a force Fa on the body, the body B always exerts also its own force on the body. So the forces Fa and Fb are equal in magnitude but opposite in direction. And since there is a vector, we can write Fa is equals to what? Minus Fb. Fa. So because they are moving in opposite direction, that is what that minus means. But their magnitude is the same. Magnitude is their size. So it states that action and reaction are equal. And what? Opposite. The opposite is where the minus sign came from. So those are the Newton's third law of motion. So this is momentum. We've explained momentum. So the measure of an object's resistance to change is its state of motion due to the application of a force. So momentum is mass in motion. Yes, because I've already explained that velocity is the speed of the mass. Because momentum is what? Mass times velocity. So momentum is mass multiplied by velocity. So mass in motion. Because velocity is about you being in motion, and that's the sign, and that is about momentum. So we have conservation of momentum. Conservation of momentum, just from the Newton's just from the conservation of energy, the law of conservation of energy. What does it say? Energy can neither be created nor destroyed, but changes from one form to another. So when we talk about conservation of momentum, it's trying to say that the momentum before and after is what? Is equal. Two objects are coming together. The momentum they had before they meet and the momentum after they meet is what's going to be conserved. That it must be equal, and that is what this conservation of linear momentum is talking about. So if two objects interact in two perpendicular directions, the total momentum of the two objects before the interaction is the same as the total momentum after the reaction in both directions. You can see it from the board. You can see what we are saying. You can see the board, this thing when they met. That is it. That's the interaction. So if two bodies interact, in two perpendicular directions, the total momentum of the two objects before the interaction is the same as the total momentum after the interaction in both directions. So when two objects interact in a single direction, the total momentum of the two objects before the interaction is equal to total momentum after the interaction. What we are just trying to say is sometimes the objects might be moving in the same direction, it's still the same. The total momentum before and after is equal. But sometimes it might be moving in opposite direction. Maybe one is coming from the left and one is coming from the right. So after meeting, the momentum before and after is also what? Is also the same. So let's go to the next slide. So conservation of linear momentum. The principle of the conservation of linear momentum can be stated in different ways in any system of colliding objects. Just look at it now. Look at these two objects now. We have M1, we have M2. They were going. These ones are in the same direction. M1 has its own force, M2 has its own force. So look at two of them now. They were coming together. Then they now met. And what happened? Both of them are now going in the same what direction, that is after collision. So this is the initial velocity, this is the what force, this one has its force, this one has its force, and this is their final velocity. This is their final velocity. So say the principle of the conservation of linear momentum can be stated in different ways. In any system of colliding objects, the total momentum is always conserved, provided that there is no net force acting on the body, on the system. The total momentum of an isolated or closed system of colliding bodies remain constant. If two or more bodies collide in a closed system, the total momentum after the collision is equal to the total momentum before the collision. So by closed system, we mean a system on which no external forces are, so it doesn't affect that system. That's what we mean by a closed system. The principle of the conservation of linear momentum follows from the third law and second law of motion. You know, the third law and second law was talking about the relationship between force and momentum, while the third law was talking about action and reaction are equal and what? And opposite. Action and reaction are equal and opposite. So look at it now. This is the force, both of them. We said force exerted by an object A is equal to the force exerted by an object B, and MA is force. MA. This V1 minus T is A, is acceleration. So M1 force is equal to force. The force before the exerted by object A is equal to the force exerted by object B, and here we can derive our motion, our linear momentum, the conservation of linear momentum's formula, because M1 V1 minus U1 is equal to what? M2 V2 minus U2. Don't forget there is a T here. T and T is going to cancel out. Yes, we are going to cancel because we have T here, we have T here. We don't need the repetition, they are the same. So the time will cancel out. Then what is going to be left? We are going to have this our M1 V1 minus U1 is equals to minus M2 V2 minus U2. Why? Because the forces are equal and opposite. Don't forget that from Newton's second law of motion. So the force exerted by object A, this is object A. This is when they met. This one's, you can see the direction of this one's first. You can see the direction, but the forces are equal, but what? Opposite. So that is what is happening, and that's why we had our minus here. So minus MV to M2 V2. Minus times minus will give us this plus, and that's why we have M2 what? U2. So M1 V1 plus M2 V2 is equal to M2 U2 plus M1 Q1, and this is the final momentum of the two objects. So momentum before collision is equal to the momentum after. So this one is before. Mass times initial for the first body, mass times initial for the second, and the one for the what? Final velocity, and thus momentum is what? Is conserved. So applying the principle of conservation of linear momentum. 1. We need to consider the object that is included in the system. The bodies that are related to the system do not identify external and internal forces. Verification of the system's isolated position. A closed system should also be ensured that the initial momentum equals that of the final momentum. That is the principle of the conservation of linear momentum. Linear momentum must be conserved. Momentum is a vector point. What are the applications of linear momentum? We have the launching of rockets. The rocket fuel burns, and after burning it does what? And pushes the exhaust gas in the downward direction. Because of this, the rocket gets pushed in the upward direction. Do you get that? Because we are talking about action and reaction. When the rocket fuel burns, it pushes it down. But what happens? It pushes the exhaust gas in the downward direction. Because of this, the rocket gets pushed in an upward direction. I'm sure if you have seen a rocket before, you will see that is how the motion goes. It goes down, then it launches back upward. Then we have the motorboats. It pushes the water backward and gets pushed forward so as to conserve the momentum. Action and reaction are equal and opposite. Walking, a person walks by pushing with his or her foot against the ground. The ground exerts an equal and opposite force back on the person. So it is the force on a person due to the reaction of the ground that moves him or her forward. This means a person walking is actually pushed forward by the reaction force of the ground on him and not by his own push on the ground. So that is it. So ice skaters, let us consider two skaters, a man and a woman. I'm sure you've seen ice skaters, those people that skate on the ice, who started from rest, that is 0, right? And then pushed off against each other on the ice. And there is less friction. Here, the woman's weight is 54 kg, whereas the man's weight is 88 kg. The woman moves away with a velocity of 2.5 meters per second. What is the recoil velocity of the man? Two of them hit. What happens to the man's velocity? What happened to the woman's velocity? That is what we are just trying to say. So let's check now. The woman moves away with a velocity of 2.5 meters per second. So don't forget, mass and velocity is our focus when we are talking about what? Linear momentum, conservation of linear momentum. So the external force is equal to 0, mv. This is mv1 plus m2v2 is equals to what? Is equals to 0. Mass times velocity is the momentum. So this is the momentum of the first body, the momentum of the second person. So v2, which is the momentum of the man, is the mass m1 that we have multiplied by what? v1 of the woman divided by m2, because we are looking for the man's what? Velocity. And doing all of that, we are going to have what? v2 to be what? 1.5 meter per second. So the recoil velocity of the man is what? 1.5 meter per second. That's the recoil velocity of the man. The recoil velocity of the man. So let's check this example. A bullet of mass 0.05 kg is fired horizontally into a 10 kg block. So we have a block and a bullet was fired into it, right? Which is free to move. If both bullet and block move with a velocity of 0.5 meter per second after the impact, find the velocity with which the bullet hits the body. So look at it now. We have a bullet of mass 0.5 kg, right? It is fired horizontally into a 10 kg block. So we have a bullet fired into a 10 kg block. But what happened? The bullet's in velocity changed the position of the block, because look at it afterwards. If the bullet and block moved with a velocity of 0.5 meter per second after the impact, find the velocity with which the bullet hits the what? The body. That is the initial velocity. Don't forget their final velocity is equal. So let the initial velocity of the bullet be u meter per second. Momentum before impact, that is the mass, right, times the initial velocity that we do not know. The mass of the bullet and block later, because afterwards two of them became together, was this. And the momentum after collision is what? The mass times their velocity. Then from conservation of linear momentum, we are able to get what? This as the what? Final. This. Let's go to the board to explain that. Let's go to our board to explain that. So this is it now. This is a bullet, right? This is a bullet, and this is a block. This block is standing here now, right? So look at it now. We don't know this block was short, and it hit this block here. This block was actually stationary, right? It was stationary, but when they hit each other, it moved this one, and both of them were now moving with the same velocity. So what is the mass? Let's check the mass of both of them. What's the mass of the bullet? The mass of the bullet was 0.05 kg. The bullet was 0.05 kg. It was moving with a particular what? Velocity, and that is the u, which we do not know. So when it met this block, this is the momentum before mass times velocity, right? When it now came in contact with this particular block, two of them's mass will be equal, will be added together. That will be what? 0.05 plus, what is now the mass of the block? Because two of them are now together. What's the mass of the block? The mass of the block is what? 10 kg, right? The mass of the block is 10 kg. So that is 10. So plus 10 is giving us the new mass. That's 10.05 what? Kg. But this is now, both of them are now moving with the same velocity. And that new velocity was what? What was the velocity that we were given that both of them are now moving with? Both of them are now moving with 0.5 meter per second. So now, its own v, which is the final velocity, is 0.5 meter per second. So that's times 0.5 meter per second. So this is the momentum before, because it was just the bullet that was moving. It came to meet this block, and then after it touched the block, it was able to push the block forward, and they were now moving with the same velocity. They were moving with the same velocity. So they are now asking us that what velocity was the initial velocity of these bullets, and that is what we are doing, and that is 0.05 u is equals to what? 10.05 times 0.5 v. Okay, we have it already. So u will be equals to 10.05 times 0.5 divided by what? 0.05, and that will give us the initial velocity of the bullet. Initial velocity of the bullet. So we have 10.05 times 0.5 divided by 0.05. Okay, 0.05, and okay, it's continuing to move with 0.05 u. Okay, divided by 0.05. Was that what we wrote there? Yes, we are right. Okay, 0.05, and then we have 100.5 meter per second as the initial velocity. I hope you understand that. Then this is another question. A body P of mass 5 kg. Okay, this body was there. It's just like someone was here. The person's mass was 5 kg. Was already moving with a velocity of 30 meter per second. It now collides with another body Q, moving in opposite direction. Moving in opposite direction. Both of them were moving in opposite direction. Look at it now. This is it. We have body P. We have body P. We have body Q. So if P was going like this, Q was coming like this, because they are coming in opposite direction. So what is the mass of P? What's the mass of Q? The mass of P was 5 kg, and the mass of P was 5 kg, and it was moving with a velocity of 10 meter per second. It was moving with a velocity of 10 meter per second. So what else? We have the Q moving in the opposite direction with a velocity of 20 meter per second. So this one was moving with a velocity of 20 meter per second. Okay, so what happened when they met? Then I said moving in opposite direction with a velocity of 20 meter per second. If both bodies now move in the direction of P at a velocity of 10 meter per second, calculate the mass of Q. So what this is just trying to explain is the two of them met. So one of them had to, once, it's just normal. If you push someone, it's either the force will also push you towards the direction of that person. So two of you hit each other, then is it that one person will fall to this direction of one person, or the other person will fall to the direction of, if A and B collide, is it that A and B will now do what? They will move in the direction of A, or A and B will move in the direction of B. So that is what has happened here. So look at both of them. Then I said calculate the mass of Q. Calculate the mass of Q. Don't forget that momentum before is always equal to the momentum what after. So M1 V1. Let's go to our board. Let's go to our board. So here now, it's going to be what? M1 U1, right? Because they are going in opposite direction, minus M2 U2. That was the initial velocity before they met. So when they now met, now what happened? This is now their meeting point. Two of them has met. So their masses will be equal. It will be 5 plus what? Plus Q's mass, right? And their velocity now is now 10. So is equals to what? Is equals to mass, right? The addition of their mass multiplied by their new velocity. So what was our M1 for the first thing? It was 5, right? It was moving with 10 minus this other one was, we don't know it, which is the M. It was moving with 20 meter per second, is equals to their mass now will be 5 plus the M that we do not know, multiplied by the new velocity, which is what? Which is 10. So this is 50, right? Minus 20m is equals to 50, right? plus 10m. You understand that? They were going separately before. They now met and were moving with the same velocity. So what we do is we have to add their mass together because they are not going separately. We have to add their mass together, then multiply it by what? We have to add their mass together, then multiply it by their new velocity, because both of them are now moving in the direction of P. They are now moving in the direction of P. So let's do that. So that will be 50 is equals to 10 the mass of the first body was m, its velocity was 20. Sorry, I'm not writing something wrong. Okay, something is wrong. It was 5. Oh, the velocity was 30 meters per second. So sorry about that. I was wondering why they were having the same. So the velocity, the first velocity was 30, and that was why both of them are now moving in the direction of P. That's why both of them are moving, because the velocity of P is more. Sorry, this was 30. So it was 30, not 10. So this is 150. Okay, so 150 minus 50 is equals to what? 10 plus 20m. 10m plus 20m. So this is 100 is equals to what? 30m. Is equals to 30m. So our m will be 100. Let me check if we have not made. Our m will be equal to, yes, we are right now. So our m will be equals to 100 divided by 30, and that gives us the mass of the other body. And what is m divided by 30? Let's check the mass. The mass is what? The mass is 3.3 kg. You can see that P had bigger mass. It also had more velocity. That more velocity. So look at it now. And later they said that they moved, both bodies now move in the direction of P as velocity, because of the velocity of P. Both of them are now moving together in the same direction. Moving together in the same direction. So that is that about. So the total momentum before collision is equals to total momentum, and we understand how we call it. This was the body. Body P is mass times velocity. Everything about momentum, mass times velocity. The only focus is the momentum before and after collision must be what? Must be equal. Must be equal. That is what we've established with what we did here. Collisions between two billiard balls or between two automobiles on the road are few examples of collisions from our everyday life. Yes, we've seen collisions a lot of time. Even gas atoms and molecules at room temperatures keep on colliding against each other. Thus, in physics, collision is said to have what occurred if two particles physically collide with each other, or even when the path of motion of one particle is affected by the other. In the collision of two particles, law of conservation of momentum always holds true, but in some collisions, kinetic energy is not always conserved. Hence, collisions are of two types based on the conservation of energy. We have the perfectly elastic collision and the perfectly inelastic collision. Elastic collisions, perfectly elastic collision. Those collisions in which both momentum and kinetic energy of the system are conserved are called elastic collisions. They are called elastic, perfectly elastic or elastic collisions. Those collisions in which both momentum and kinetic energy of the system are conserved are called what? Elastic momentum. That is, the momentum is conserved and kinetic energy, which is half mv square, also is conserved. That is what called what? Elastic collision. So characteristics of elastic collisions: total momentum is conserved. Don't forget, your momentum is what? Mass times velocity. Total energy too is conserved. Total kinetic energy is conserved, and total mechanical energy is not converted into any other form of energy, and that is the characteristics of elastic collision. Consider two particles whose masses are m1 and m2 respectively, and they collide with each other with velocity u1 and u2. That is their initial velocity. Two masses, just look at them. Two people, m1 and m2, then they collided. Two cars, one was coming from Ibadan, one was coming from Lagos, and they collided respectively, and they collide with each other with velocity u1 and u2. That is, car 1 was coming with one velocity, car 2 was also coming with a speed. Velocity is like speed, without the what? Direction. So they were both coming. Then when they collide, what happened? Their velocity will become v1 and v2 respectively. If the collision between these two particles is elastic, Then from the law of conservation of momentum, we have m1u1 plus m1u2 is equals to what? m1v1 plus m2v2. We already have that. Momentum before and after is what? Conserved. And from the law of conservation of energy, their kinetic energy too must be conserved, because you know kinetic energy is half mv square. We can remember that. So half mv square for the first body plus half mv square for the second body before meeting is equals to half mv square after meeting of the first car and half mv square of the second car. So that is just what this is telling us about collision. Their energies. For when you are deciding what type of collision, you have to consider the energy. It's not only about knowing if the momentum is conserved. The kinetic energy too must be conserved. And this is the formula for kinetic energy. For the first body plus the one for the second body, this is before they met. Then when they now collided, bash, the momentum of the first body and the momentum and the kinetic energy of the second must be the same thing. And that is where we have perfectly elastic collision. So we have the second one, which is a perfectly inelastic collision. So this one is just like the opposite. Those collisions in which the momentum of the system is conserved, but the kinetic energy of the system is not conserved. Just know that. For the perfectly inelastic collision, momentum is conserved, kinetic energy is conserved. But for these ones, those collisions in which the momentum of the system is conserved, but the kinetic energy of the system is not conserved, are known as inelastic collisions. Here, in an inelastic collision, two bodies stick to each other after collision as a bullet hits the target and remain embedded in the target. In this case, some of the energy is converted into heat energy or is used up in doing work in deforming bodies. For example, when two cars collide, their metal parts are bent out of shape. So what are the characteristics? Yes, the total momentum is conserved, the total energy, yes, is conserved, but the total kinetic energy is not conserved. A part or all of the mechanical energy may be converted into other forms of energy. So some or all of the forces involved during interaction are non-conservative in nature. So consider two particles whose masses are m1 and m2 respectively, and they collide with each other, right, with velocities u1 and u2 respectively. If the collisions between these two particles is inelastic, and these two particles will stick to each other, and after the collision they move with velocity v, and these two of them will move with one velocity, then from the law of conservation of momentum, we have this was the two of them before they met. m1 u1 is equals to plus m2 u2 is equals to m1 plus m2. Then they will both be moving with the same velocity. They will both be moving with the same velocity. That is inelastic collision. You can see them. So both of them will be moving with the same velocity, and that's why we have it like this. The kinetic energy of particles before collision is, for the first particle is half m1 u1 square plus half m2 u2 square. For the second body, it is the addition of the two. It's not equal to each other because it is not conserved. So by law of conservation of energy, this plus this is equals to this plus this, then plus q, where q is the loss in the kinetic energy of the particles. You can see that this side is not equal to this side because there is an addition of the loss in kinetic energy added to it. So example, two bodies A and B of masses 4 kg, as we can see, we have it in the diagram, and 2 kg move towards each other. They move towards each other. This one is just like a car traveling. This one is coming from Ibadan. This one is coming from Lagos, and they were traveling with what different velocity. This one's velocity was 3 meters per second. This one was 2 meters per second. This one's mass was 4 kg. This one's mass is 2 kg. And don't forget what you said. When they meet, you can see that the mass, most times they will move in the velocity with the body that is having bigger mass. Because this one will push it forward. Look at it, it's speeding more. This one is running faster, and it's also having more mass than the other one. So definitely they will be moving in its own direction when two of them hit each other. So two bodies A and B of masses 4 kg and 2 kg move towards each other with velocity 3 meters per second and 2 meters per second and collide back. If the collision is perfectly inelastic, what does that mean? Look at them, they are now having one velocity. Find the velocity of the two bodies after the collision. Then find the total kinetic energy of the system before and after collision. Hence, calculate the loss in kinetic energy. Very simple. We know whenever we talk about momentum. Mass times velocity is what comes to our mind. So we have to tell, okay, what happened before collision? These two places were before collision. This bigger one is when they've collided. You see that the box is bigger when two of them are now together. And we can say we added their masses together. So before collision, there was mass times velocity for the first one. Because they are moving in opposite direction, we have the minus sign. So 2 times 2 for the other one is equals to, this is before collision, is equals to after collision, right? So 4 plus 2 is equals to this, V. So before collision was 8, after collision was 6V. So were we able to get our V? Yes, we were able to get the velocity they were now moving with. And the velocity was 1.33 meters per second. That was the velocity two of them are now moving with. Why? Because they've collided. And that is the velocity. So kinetic energy before collision is just what is happening here, right? So half mv squared for this body plus half mv squared of this other body. So 1/2 mass 4 v 3 squared, then plus the other one half mv, ke is half mv squared. Don't forget that then 1/2 the mass 2 multiplied by the velocity 2 squared, and this is the energy ke, kinetic energy before collision that two of them had. Then after collision, both of them are now moving with the same velocity. It means we have to add what? Their masses. So we have what? Half what? Ke, half m, which is 4 plus 2, right? Because they are moving with the same velocity. Half m, then v squared, half mv squared. For the first one, we have 1/2 x, 1/2 times, 4 plus 2x multiplied by 1/2 multiplied by 2 times what? 1.33 squared, and that gives us what? 5.33 joules. 5.33 joules. This is after collision, and that is equals to what? 22 minus what? 5.33 joules, and that gives us what? 16.67 joules. 16.67 joules. So this is the collision after, and this is not supposed to be there. It's supposed to be 1/2 times 6 multiplied by 5.33 squared. This part is not supposed to be there. It's supposed to just be collisions after. So ek2 is supposed to be, because they are now moving with addition of their velocity and moving with one velocity. So this part is not there. This part is not there. It's just 1/2 plus multiplied by 4 plus 2 multiplied by their velocity. The velocity that now both of them are now moving with is this. Both of them are now moving with 1.33 meter, and that's what we have here, and it will give us. So the loss in kinetic energy is 22 minus 5.33 joules. Minus 5.33 joules. So what we're supposed to have was supposed to be 1/2 times 6x, 6 here, multiplied by 1.33 squared. This part was an error. It was a mistake from it was a typographical error. So this is just the collision after, because they are now both moving in the same direction and with the same velocity. So what do? We have to add their mass together, which is 4 plus 2 multiplied by, because it's half m v squared. This place is not there. It's half m v squared, and that will give us this. And when you subtract it, we are going to get the loss in kinetic energy. So name instances where Newton's law of motion comes to play. Newton's law of motion. What instances do you think Newton's law? We've already explained the first one. We've already explained the first one when we were talking about a football being at rest. Then a footballer came to kick it, and what will continue to be at rest until when what happens? When net stops it, and that is what application of Newton's law of motion. So you can think. So can you think of scenarios where Newton's third law of motion is relevant? Provide examples of where Newton's second law of motion is applied. Contact forces and non-contact forces. So you know what contact forces are? They are forces that requires what objects to be in physical contact with one another, while non-contact and one that does not require that. You know, contact forces is pull and push. Non-contact force, we have the magnetic force, we have the electrical force, and we have the gravitational pull or gravitational force, and that is that. So thank you for this class, and see you in the next